In this video, let's see Twig and link matrices, relationship between number of trees of a graph and reduced incident matrix, and finally the relationship between branch voltages and node voltages. Let's see all these things in detail. First of all, let's see how to generate Twig and link matrices from reduced incidence matrix of a graph. For that, let's consider an oriented graph as shown here. As seen here we can have 4 nodes and 6 branches, and orientation of each branches is shown here. Now, first of all, let's see what is the complete incident matrix and reduced incident matrix of this particular graph. As we know, in the case of incidence matrix, complete or reduced, here the column represents branches and rows represents number of nodes. As we can have 4 nodes and 6 branches, the size of this complete incident matrix AI is 4 by 6. So when we are considering node 1, the incident branches are 1, 2, 6, corresponding entries are 1 and remaining entries are zeros. As the current direction in all these branch which is incident to node 1 is going away from this node, their sign is positive. Similar way, when we are considering node 2, the incident branches are 2, 3, 4. Here 2 and 4 branches are incoming towards this node 2, therefore their sign is negative, and corresponding to 3 it is positive and remaining entries are 0. Likewise, we can find out the entries corresponding to node 3 and node 4 and which can be obtained as here. Now, we can build reduced incident matrix. How to generate reduced incident matrix? By removing any one row of this complete incident matrix, we can generate reduced incident matrix. Usually we are preferring the last node, that is reference node. It is possible to remove any other rows also. So here we considered to remove third row. So after removing third row, the remaining entries are these first 2 rows and the last row as shown here. So this is the reduced incident matrix corresponding to this graph when we are removing third row entry of complete incident matrix. Now what we are going to do is we are selecting any one tree. We know a graph may contains many number of trees. The relationship between number of trees and reduced incident matrix we are going to see later in this video itself, and we will solve some problem based on that one. So anyway, let's consider a tree from this graph. So we can consider a tree like this. So this is the tree, that is green one represents tree. We know complement of tree is nothing but co-tree. So what is the name of tree branches? It is known as twig. How many twigs are there? We can have 3 twigs, that is 2, 3 and 4, that represents twig. That is branches of trees are branch 2, 3 and 4. We know the relationship between number of twigs and nodes. So number of twigs is equal to n minus 1. So total number of branch is B. Among these B branches, n minus 1 branches corresponding to twigs. So what is the number of links in general? It is total number of branches minus number of twig. So it is obtained as B minus n minus 1, that is B minus n plus 1. The co-tree branches are usually termed as links or chord. Here 1, 5, 6 are co-tree branches, or it is links. They are links. So we select a tree like this having branches 2, 3 and 4. Now what I am going to do is I am going to arrange the column entries corresponding to this reduced incident matrix in such a way that first 3 columns. Why? Because the number of twig is n minus 1. Here number of node is 4. So n minus 1 is 3. So first 3 columns corresponding to twig and next 3 columns are corresponding to links. So we are arranging the column entries of this reduced incident matrix in such a way that First column entry is corresponding to second column of this matrix, then third column will come, then fourth column will come. Then after that link column will come, that is corresponding to 1. It will come over here. Next it will come fifth one and sixth one as shown here. So what is the second column entry? It is coming as the first column entry in this arrangement. Similarly, third one. This third entry is copied over here. Then fourth column entry is copied over here. Then first column entry is coming to here. Fifth one and sixth one is already retained as such. Now this part is a submatrix of this reduced incident matrix A. Similarly, this part alone when we are taking, that is another submatrix of this reduced incident matrix. Here what we done is we are just rearrange the column entries like this. So this submatrix is known as Twig matrix and this submatrix is termed as link matrix. So we can write down this reduced incident matrix in this manner. That means reduced incident matrix is subdivided into two submatrix. They are Twig matrix and link matrix. Now let's see what is the determinant of Twig matrix. The entries corresponding to Twig matrices are separately shown here. So this is 1 0 0 minus 1 1 minus 1 0 minus 1 0. When we are finding out the determinant of this one, 1 into determinant of this one, so 1 into 0 minus 1 will come and remaining entries are 0, so the determinant is minus 1. So when we are taking Twig matrix of any graph, in general we can say that the determinant of Twig matrix is either plus 1 or minus 1. In this case it is obtained as minus 1. So when determinant of a matrix is 0, what is the name of that matrix? That matrix is singular matrix. So if determinant of a matrix is not 0, it indicates that that matrix is always non-singular matrix. So the Twig matrix is always non-singular matrix. Another important point regarding this Twig matrix is that rank of Twig matrix is equal to rank of reduced incident matrix, that is equal to n minus 1, where n is number of nodes of the graph. Now let's see the relationship between the number of possible trees of a graph and reduced incident matrix. So this is the relationship between number of possible trees of a graph and reduced incident matrix. So if we are finding out the determinant of product of A and A transpose, that gives number of possible trees of a graph. This is very, very important. So let's see this relationship with the help of a problem. So the question is, obtain the oriented graph of the incidence matrix shown below. Also, we need to draw all the possible trees of this graph. How to say that this matrix is reduced incident matrix or complete incident matrix? For complete incident matrix, the sum of all column entries will be 0. Let's see that one. So here the sum is 0, here the sum is 0, here the sum is not 0. So it is a reduced incident matrix. Now, first of all, we need to draw the graph. Why? Because we need to draw all the possible trees of this graph. So first of all, we need to build the oriented graph of this incident matrix. So let's generate the fourth rows entry. So it is here, it is already 0. Second column also its entry is 0, sum is 0. Here, in order to make sum to 0, this entry should be minus 1. Here also the entry should be minus 1. Here also the entry should be minus 1. Now we got the relations. What is the number of nodes? Number of nodes is 4. That represents number of rows. Similarly, how many branches are there? This is branches. How many columns are there? 5 columns are there. So that represents number of branches. Now let's see this relation. How branch 1 is connected. Branch 1 is connected between node 1 and 2. So it is going away from node 1 and coming to node 2. So like this. So the current direction is in this manner. Similarly, when we are considering branch 2, this is branch 2, how it is connected? It is connected between node 2 and node 3. What is the direction of current? Current is leaving from node 2, that's why this is plus, and entering into node 3, the direction is 2 to 3. The current direction is 2 to 3. Similarly, when we are considering branch 3, it is connected between 3 and 4. It is connected between 3 and 4. What is the direction of current? It is going away from node 3 and coming into node 4. So the direction of current is like this. Similarly, when we are considering branch 4, it is connected between 2 and 4 and the current direction is shown here. Similarly, fifth branch is connected between 1 and 4. And it is going away from node 1 and coming into node 4. So its direction of current is like this. So when we are combining all these things, the oriented graph is somewhat like this. Here we can have 4 nodes and 5 branches. We already found the relationship between number of possible trees and reduced incident matrix. So number of possible trees of this graph can be obtained by means of this expression, determinant of the product of A into A transpose. This is our A matrix and transpose is this one. When we are finding out the product of A transpose, we can obtain this matrix. Now we need to find out the determinant. Determinant is obtained as 8, 10 minus 2, 8 will come. That means by means of this graph, it is possible to draw 8 trees. What is tree? We can travel from one node to every other node through a path without any closed path. So in this oriented graph, it is possible to draw 8 trees. So these are the possible tree which we can draw by means of this graph. So I am giving one homework to you similar to other 2 videos. So here the question is same, the reduced incident matrices just changed. So please solve this one. Next, let's see the relationship between node voltages and branch current. Consider a graph shown here for analyzing the relationship between node voltage and branch current. We have already applied KCL at each node of a graph for obtaining incident matrix of a graph. The KCL equation can be represented in matrix form as here, that is matrix A into matrix IB, that is branch current matrix, is equal to null matrix 0. So let's consider this graph. For this graph, complete incident matrix is obtained like this. When we are removing any one row entries from this complete incident matrix, then that matrix is known as reduced incident matrix. Here I removed the last row. So this is the reduced incident matrix. So when we are applying KCL at node, so the matrix representation of KCL equation is like this. Here the size of A matrix is n minus 1. Why? Because we removed one row. So n minus 1 into B. And size of branch current matrix is, how many branches are there? Here we can have 6 branches and 4 nodes. IB matrix size is B by 1. In this case, it is 6 by 1 as shown here. And this is a null matrix. Its size is n minus 1 into 1. So this is the matrix representation of KCL equation. Now what I am going to do is, here we can see node voltages are there and branch voltages are there. So branch voltages are represented their polarity by means of current direction. So as current is flowing from higher potential to lower potential, this potential should be higher compared to this point. So likewise, I mark all the branch voltages. Now let's consider node 1, node 2, node 3, node 4 voltages be represented in this manner, V1, V2 and V3. As we are considering the fourth node as the reference node, its potential or its voltage is 0. V4 voltage is taken as 0. And as I marked, the branch voltages be represented by VB1, VB2, VB3 all the way up to VB6 as shown here. Then from this graph, what is VB1? VB1 is equal to V14. V1 minus V4. VB1 is equal to V14. That means V1 minus V4. What is V4? 0. So it is V1. Similarly, what is VB2? VB2 is this one. As the current is flowing in this direction, its higher potential is marked over here, and this is a lower potential. So what is VB2? VB2 is V4 minus V2. This node voltage minus this node voltage. As this voltage is 0, 0 minus V2 will come. 0 minus V2 will come, that is minus V2. Okay. Similarly, when we are considering VB3, this is VB3. What is VB3? V23, that is V2 minus V3. Similarly, when we are considering VB4, which is equal to V1 minus V2. Similarly, V5 is equal to V3 minus V4, that is V3 itself. Similarly, VB6 is equal to V1 minus V3. Now, let's arrange this equation. Say this is equation number 1. Let's arrange this equation in matrix form. How many branch voltages are there? As we can have 6 branches, 6 branch voltages will be there. So this matrix represents branch voltage matrix. Clear? This matrix represents branch voltage matrix. And when we are arranging these coefficient of node voltages corresponding to each branch voltages in matrix form, so this is the matrix form representation. That is nothing but your reduced incident matrix transpose. So this is our reduced incident matrix, this matrix. So it's just transpose is obtained as the coefficient of these node voltages corresponding to these branch voltage equations. So in general, we can say that VB branch voltage matrix is equal to incident matrix transpose into node voltages. Okay, so by KCL we can have two matrix relation, that is branch voltage is equal to reduced incident matrix transpose into node voltage, and KCL equation is A into IB matrix is equal to null matrix, that is reduced incident matrix into branch current matrix gives null matrix. This is the KCL equation, and this equation represents the relationship between branch voltage and node voltage in terms of reduced incident matrix.